Let's see if we can learn a thing or two about SN2 reactions. And you're going to see a lot of these in organic chemistry. And this sounds like a very fancy term, but it really just stands for, the S stands for substitution. Substitution. The N stands for nucleophilic. Nucleophilic. And then the 2, and this is probably maybe the least obvious part of SN2. The 2 comes from the fact that the rate determining step in this reaction involves both reactants. And I'm going to show you what we mean, and it'll actually be probably more clear when we compare it to SN1 reactions. So let me show you an SN2 reaction. So let's say we have bromomethane. So and let me draw it in 3 dimensions. So you have a hydrogen sticking out. Maybe the bromine is right over there. And then you have another hydrogen in the back. And then you have a hydrogen that comes up just like that. And here, the 3 dimensions won't matter that much. This is not a chiral carbon. There's no handedness here. But in the future, we'll think about chiral carbons and what might happen to them as they undergo SN2 reaction. So I have this bromomethane here, and let's say we also have some hydroxide in solution with it. So it's a hydroxide, and this oxygen has 7 valence electrons. You can imagine that the way that you get a hydroxide is if you start off with water. If you just start off with water that looks like this. If you start off with water that looks like that, and maybe there's another water someplace. Maybe there's another water someplace else that looks like that. And maybe in one step, this water right here takes this guy's hydrogen. Remember, there's a partially positive charge on the hydrogen, partially negative charge on the oxygen. So maybe he gives one of his electrons to the hydrogen, which will end up with a positive charge. It'll be a hydronium cation. And then this electron takes back that extra electron from the hydrogen. And so now he's going to have 7 valence electrons. He's going to have this one that was at this end of the bond, the one that he's taking back, and then that's 2, 3, 4, 5, 6, and then this electron right there, 7. So he's going to have 1, 2, 3, 4, 5, 6, 7 valence electrons. He's going to have a negative charge. It's neutral when it's water. When he takes an extra electron, it's going to have a negative charge. And you can imagine this is in a solution with water, that water is our solvent. So let me put a negative charge right here. I could write -1 if I want. And in this reaction, just so we know what's what, this hydroxide molecule, or this hydroxide anion, is our nucleophile. It is the nucleophile right there. Nucleophile. And the best way to think about a nucleophile is it likes other people's nucleuses. It likes them because nucleuses are positive. It has an electron. It has extra electrons. In this case, it has a negative charge. So it is attracted to other nucleuses. Nucleuses of atoms are positive. So it is attracted to electrons. Phile, I'm not a Greek scholar, but it means, like to be attracted or to like something. So it likes nucleuses. And if you want to compare it to acid or base, this would actually you would classify this actually as a Lewis base, something that gives electrons. But we're not going to go into that right now. This is a nucleophile. It is attracted to nucleuses, to positive things. It wants to give away electrons. Now, what's going to happen is that this is going to give an electron to this carbon. This carbon is going to say, oh, I got an electron. Let me give away an electron to somebody who probably wants it really badly. And in this case, it's going to be the bromine, because we've seen multiple times that the bromine is very electronegative. It already is starting to hog the electrons, and it would like to take an electron altogether. And so let me show you the reaction. It's going to happen very quickly. Or it's actually going to happen very quickly the way I drew it, because it's really a one-step reaction. So you're going to have one of these electrons right here. One of these electrons will attack the carbon, or I shouldn't say attack, that sounds very aggressive. It will be given to the carbon. And then the carbon says, oh, I'm getting an electron from this direction. It actually has a slightly positive charge at this end because the bromine is hogging some of the electrons. So they'll be attracted to each other. They're going to bump into each other just the right way. And then the bromine, and then at the exact same time, this all has to happen kind of simultaneous. At the exact same time, this electron that's sitting at that end of the bond is going to go to the bromine. And so what is it going to look like when this reaction has actually occurred? So let me just, so it is literally a one-step reaction. So you have your carbon, you have the hydrogen that is pointing up. You have the hydrogen that's pointing up. Now let me color code this, just because that'll make it interesting. So you have this hydrogen that is coming out of the screen. So now you're going to have this hydrogen coming out of the screen. And it's still just coming straight out of the screen, but I'm going to draw it to the down right because this hydroxide's attacking from behind. And this bromine, which we call the leaving group, or actually it's going to be a bromide anion once it leaves, that's going to leave from the right. Attack from the left, leave from the right, from different sides. So then this is that hydrogen that's sticking out. The hydrogen in the back, well, we know it's in the back, so I'll just continue to draw it. I'll just draw it in the back like that. And now this hydroxide is going to be attached to the carbon. So this carbon now gets one of those electrons. It now gets one of those electrons. And it is bonded now. It is bonded now to the oxygen. So let me draw the oxygen. So you have the oxygen. Let me see the best way that I could do this. So you have the oxygen here bonded to a hydrogen. And let me draw its valence electrons. So it had 1, 2, 3, 4, 5, 6. And then it had a seventh electron. It had a seventh electron, but it just gave it away. So that seventh electron is going to bond with this one. They were already a pair over here. Let me make it very clear. Let me make it very clear with the colors. This electron right over there is this electron. But it was already paired with this guy. So when he gives it away to the carbon, it forms this covalent bond right here. So now you have this OH group, this hydroxyl group, off of the carbon now. And now the bromine. The bromine, you had a negatively charged group here. Now, what I've drawn so far, everything is neutral. So something has to be negatively charged. It's going to be the bromine, because that's what's getting the electron. So now the bromine, if I wanted to draw bromine's valence shell before, it would have 7 electrons. So 1, 2, 3, 4, 5, 6, 7. Now that it's taking that electron from carbon, it's going to have 8. 1, 2, 3, 4, 5, 6, 7. And let me color code it again. So this electron right here, when it goes to the bromine, is going to be that electron right there. And we're going to have a negative charge. And so here, in this situation, just to make sure this is the nucleophile, the bromine right here, this is the leaving group. The leaving group. And then the carbon, I guess the thing that is reacting, that's getting substituted, that where the bromine leaves it and the hydroxide joins it, that's called the substrate. So I could draw it like this. This is the substrate. And the whole reason why I did it, this was not a chiral carbon, but you can imagine once we deal with chiral carbons, when they undergo an SN2 reaction like this, their chirality will actually change. So I'll leave you there right now. That'll, it gives you something to think about SN2 reactions. And then in the next video, we'll think a little bit about SN1. Oh, and before I leave you, I left you hanging on the 2. I said, this is called, it's substitution. You saw that the bromine was substituted by the hydroxide. It's nucleophilic. It involved this hydroxide, which likes nucleuses. And then I said it involves, the rate determining step involves both reactants. And here it might not be completely clear, but the rate determining step was actually what's going on right here. And if I were to draw an intermediate, so you could actually draw an intermediate step here. Let me copy and paste this. Let me paste it. So let me put it down here. So you could actually draw an intermediate step. So let me copy the other one. So let me copy this, copy and paste. So you have the other. This all happens over one step. But if we wanted to show what happens in between, for a small amount of time, you have this transition state where the carbon is going to have a partial bond. So it has this hydrogen in blue. Let me draw it. This hydrogen in blue sticking out. And then it has another hydrogen behind it. So it has this other hydrogen behind it. I'll draw it like, right. It's right behind it. And then for some small fraction of time, it is bonded to both the bromine. So I'll draw it with the dotted line. It is bonded to both the bromine, which now will have a partial negative charge because it's starting to get an electron, and it's also bonded. It's also bonded to the hydroxide. So it's also bonded to the hydroxide, which also has a partial negative charge. You can imagine this negative charge is now getting split between the two. This is a transition state. And the notation for a transition state, you put brackets around it, or parentheses in some cultures they call them, and you write this little symbol up here. This tells us this is a transition state. This is not one of the, I guess, semi-stable intermediates. This is something that we're going through. But this is an SN2 reaction because this transition state is actually what determines the rate of the reaction. This requires, I guess this is the highest energy state of this reaction. This is what's going to, well, I said it already, determine its rate. And in this transition state, this rate determining step, you have all of the reactants. You have your hydroxide right there, and you also have your bromomethane that we started with. So it has two of the reactants. That's why it's called an SN2 reaction.